In this lecture here, we want to continue talking about some fundamental concepts of algebra and introduce the concept of sets. Okay, so what is a set in mathematics? So a set is a collection of objects whose contents can be clearly determined. So it's a set of objects, okay? And sometimes, in our course, it can be a set of numbers, okay? That's in algebra, that's mostly what we'll think about it, but it doesn't have to be numbers, okay? So the objects in the set are each called elements of the set, and we use these special bracers here to indicate you are representing a set. Like you can have the set of my name and my wife's name. You could have the set of Matt and Ashley. Okay, all right, and this is just the set of names in Professor's house. Okay, but we're going to mostly use numbers, okay? So we use this. So this right here, this is the set of 1, 2, 3, 4, 5, and then you see these triple dots. An example of what's called the roster method of a set. Okay, so the roster set is literally just the list of all the elements. The 3 dots here after the 5, okay, this is called an ellipsis. These dots, ellipsis. And they indicate that there is no final element and that the list goes on forever. And it continues that the pattern you're seeing. So for example, the next element would be 6, then 7, then 8, and so on. Now, if a set has no elements at all, right, it's called an empty set or the null set. So if there's 2 ways we can show it. So you can show it with this symbol, like this, or sometimes you might see it as this bracers. These special bracers here with nothing in it. Okay, so when you see that, that just means it's an empty set. It's a set of no elements. Okay. So we have roster method. We also have what's called set builder notation, and the elements of a set are described but not listed. That's what set builder notation is. And so you see something like this. Okay, you have these bracers, and then this is saying, when you see this first thing, this is saying the variable x. So it's the set of all x. This line here means such that, so now we're going to define what x is. And then x is a counting number less than 6. Okay, so we know then if you were to write this in roster notation, it's just this. The counting number is less than 6. Well, that's 1, 2, 3, 4, and 5. Okay. So there's 2 ways to show it. So roster method is really good if there's a very distinct pattern or a small number of elements. The set builder notation is used generally when there's a larger number of elements. Okay, so now we want to perform operations on sets. So the first operation on set is what's called the intersection. So the intersection of 2 sets, A and B, all right, written as A, and then this sign here means intersection, is a set of elements common to both set A and set B. Okay, so this definition can be expressed in set builder notation as following: A intersect B, all right, is all x such that x is an element of A and x is an element of B. So for example, let's say set A is the numbers 2, 4, 6, 8, and 10, and set B is the numbers 3, 4, 5, 6, and 9. A intersect B. Well, you look, what numbers do they have in common, right? They both have the number 4 in common. They both have the number 6 in common. And that's it. So it would just be the elements that they have in common, okay, or that overlap. So this would just be 4, 6. Right? Let me do another example of this. So if I say find the intersection of the sets 3, 4, 5, 6, and 7, and 3, 7, 8, and 9, well, what elements do they have in common? Right? They both have a 3, and they both have a 7. And that's it. So the intersection would be the set 3, 7. So now we can have what's called a union. So again, this is an operation on sets. So the union of sets A and B is written as A, and then this thing that looks like a U, but this means union, is a set of elements that are members of set A or of set B. or of both sets. Okay, so it's basically, think of it as like a joining. You push them all together. Okay, but now here's the thing: you don't double count things, and I'll show this in the first example. Okay, so this definition can be expressed as A union B is the variable x such that x is an element of A or x is an element of B. So you can find the union of set A and B by listing the elements of set A, and then we include any elements of set B that are not already listed. Okay, so enclose all elements that are listed with bracers and show that as the union of two sets. So for example, if set A is the numbers 1, 3, and 5, and set B is the numbers 1, 2, and 4, A union B, well, they both have a 1, so you'd only list it once. And then you'd go 2, 3, 4, and 5. So you just like basically combine them, and then you don't double count. That's the way to think of a union. So here, let's find the union of those sets that I had before: 3, 4, 5, 6, and 7. Union with 3, 7, 8, and 9. So to find the union of both sets, you start by listing the elements of the first set, which are 3, 4, 5, 6, and 7. Now list all the elements of the second set that are not in the first set. Well, so 3 is in the first set, 7 is in the first set. So I'm going to be adding to this set 8 and 9. So thus the union of these two sets are the numbers 3, 4, 5, 6, 7, 8, and 9. All right, so now I want to talk about sets of real numbers or different, how we define different types of numbers. Okay. So I do talk about real numbers, but later on in the course we will talk about imaginary numbers. Okay. So the sets that make up all the real numbers are the set of the natural numbers. Okay, so these are 1, 2, 3, 4, 5, so on and so on. Whole numbers include 0, so it's 0, 1, 2, 3, 4, 5, and so on. Integers, think of it as the whole numbers and their opposites. Okay, so it's the numbers -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. So it goes to negative infinity and it goes to positive infinity here, but just as whole numbers and their negatives. Then we have what's called rational numbers. And rational numbers are any number that can be expressed as a fraction of two integers. Okay, so rational numbers are A divided by B, where A and B are integers. So, for example, an example of a rational number would be 7 over 2 or 12 over 5, things like that. The set of irrational numbers, okay, that's the last thing that make up real numbers. Irrational numbers cannot be expressed as the quotient of integers. So something like an irrational number would be the number pi. Okay, it's a number that has repeating or decimals that go on forever in no repeating pattern. Okay, so just looking at this, the set of the natural numbers, the set of the whole numbers, the set of integers, the set of rational numbers, and the set of irrational numbers are all subsets of real numbers. So if you look here, we have the natural numbers, which is a subset of the whole numbers. Whole numbers are a subset of integers. Integers are a subset of rational numbers. Okay, and then irrational numbers are on their own, but they are themselves a subset of real numbers. All right, let's just work some quick examples about recognizing these subsets here. So consider this set here. We have -9, -1.3, 0, 0.3 repeating. So this bar over it means the 3 keeps repeating. All right, pi over 2, the square root of 9. Just remember that's the number 3. All right, and the square root of 10. Right, and just so you can get an idea of what the square root of 10 looks like, it looks like this. Okay, so think about, do you see a pattern here? Maybe not. Not sure. All right, so we'll talk about it. List the numbers in the sets that are the natural numbers. Okay, so going back, natural numbers, 1, 2, 3, 4, 5, 6, 7, so on like that. So the only one here is the square root of 9, which is 3. So that the natural number here is just the number 3. List the whole numbers. Remember, the whole numbers include 0 and then the natural numbers. So I have a 0 and a 3. So those are the natural numbers from this set. Let's do the integers now. Okay, so the integers would be -9, 0, and 3. Okay. So what we got to do next? We got to do the rational and irrational. So the rational numbers are numbers that can be expressed as a fraction of two integers. Well, there's a bunch here. Okay, -9. You're then like, well, isn't that just an integer by itself? Well, -9 can be written as -9/1. -1.3, that's -13/10, right? 0.3 repeating is 1/3. And the square root of 9 is 3. Okay, and so that can be expressed as 3/1. So that's a rational number. Go on here then. The only irrational numbers that are left then are pi/2. And when you look back at the calculator here, there is no discernible pattern to this. Okay, these decimals will just keep going on forever. So the square root of 10 is an irrational number. All right, class, I hope this lecture helped understand the concept of sets and then different types of number systems.